Hi everyone, my name is Karn. Today I'll be presenting the paper Autonomous In-Situ Soundscape Augmentation via joint selection of masker and gain, which was a work I did while I was at NTU, Singapore. To begin with, let us explain what soundscapes are. Soundscapes, as defined in the ISO 12913 standard, is defined as acoustic environments, as perceived or experienced and or understood by a person or people in context, which means it's not just the acoustic stimuli themselves. So soundscape augmentation is a noise mitigation technique based on informational masking. So we want to improve the perception of a soundscape, especially when there's a lot of noise. So instead of trying to remove sound in soundscape augmentation, we are actually not trying to reduce the sound pressure level, and we actually are adding sound to the environment to really try to improve how it felt like or how it is perceived. However, because this is something experienced by human, it can also subjectively vary in effectiveness. A key ingredient in soundscape augmentation is the selection of masker, which is what we are adding into the environment, and also how it is being played by. And these choices are usually based on either potentially idiosyncratic, like expert opinions, using just one or two experts, or using subjective listening tests, which can actually be really time-consuming and labor-intensive, and it is also really expensive. And like even with these choices, even when done really well, these are generally static choices with very little flexibility for changes in the acoustic environment. So it actually would be nice to let a system autonomously choose masker and playback parameters based on the real-time in-situ context that we are trying to optimize for. So in an earlier work, we actually used deep learning model to perform autonomous soundscape augmentation, or rather masker selection, without considering playback parameter based on the acoustic context. This was our work in the last ICASSP. This work will tackle judge selection of masker and gain level based on the acoustic context as well, and this is the work that have been deployed across Singapore. So in the older work from last ICASSP, actually, the model actually require audio signal of pre-mixed augmented soundscape as an input, which means we already have to mix the masker with the base soundscape at particular gains, which is actually quite computationally inefficient if we are querying a large number of masker and gain combination. Moreover, in a deployment in-situ deployment setting, the masker and soundscape are not going to be combined exactly at this time alignment. By the time that the soundscape and then the decision for the masker and gain comes out, the base soundscape would have become slightly different even if it's distributionally the same. So we don't want the model to be too dependent on this particular time alignment. So what if instead of augmenting soundscape at audio level just to create the inputs, what if we could augment the soundscape at feature level by letting the model emulate this process? So this is how our proposed method looks like. The base soundscape and the masker are each transformed into log-mail spectrogram. Each of them is then passed through a convolutional feature extractor, which is known to work very well for mail spectrogram data. So we have embedding vector K from the soundscape and embedding vector Q from the masker. These two plus the masker log and gamma is then combined and quote-unquote augmented at the feature augmentation block FG. This gives us the embedding vector V. Q, K, and V are all time series embedding. So we combine them using any QKV attention block really in order to summarize it into a single embedding vector, which is somewhat independent of the time alignment between the base soundscape and the masker. Finally, the output of the attention block is then passed into the output block to produce the distribution of the perceptual quality metric that we are trying to predict from this particular augmented soundscape. In practice, our masker, which normally come from a masker bank, can actually all be computed beforehand and then stored like as a feature in the deployment unit. With each new block of audio data from the microphone sensor, the base soundscape feature K can then be computed, and then all of this information plus the candidate logins can just be used to compute and then output the rest of the predicted distribution, which can be much more efficient than actually passing each pair one by one through the model. But there is one detail that I haven't gone through, which is how exactly we implement the augmentation block. So the augmentation block emulates what the feature of the augmented soundscape would look like if there actually were a feature extractor for it. We try a few different ways. One way is concatenating the features together and then pass it through a dense block. Another way would be to treat the embedding as if it is like an audio signal and mix them up using an addition. And another way would be to stack them up onto different channels and then pass it through a convolutional layer and then followed by a dense layer. We will see how each of these combinations affect the result later on in the result section. Since we are training a probabilistic model here, we just go with the maximum likelihood formulation, where we treat the quote-unquote ground truth, which is the rating from a human rater, as an observation, and we try to maximize the log likelihood of those observations through the predicted distribution outputted by the model. So using an Gaussian assumption for the rating, the loss function is essentially almost like a regularized mean square error. And in this work, we are optimizing for the Pearsonness using data from the Arouse dataset version 1, which we recently published in the Transaction on Effective Computing. Now that we have trained the model, we are looking at the prediction error in terms of mean square error and mean absolute error for the Pearsonness rating, which is normalized between -1 and 1. On the x-axis, we see different type of attention or not using attention at all, which is essentially just using V as an embedding before going into the output block. We can see the different kind of attention, additive attention or Badenow, dot product attention or Luong, or multi-head attention commonly used in transformer. They do not have that much difference as long as there is some kind of attention there to couple the three embeddings together. In terms of feature augmentation, we can see that convolutional augmentation actually works the best. We believe because the convolution filter actually allows neighboring part of the time series to see each other and different part of the embedding to see each other through the kernel and align the feature over the dimensions. So this is actually quite helpful for combining the feature into something that is meaningful for downstream prediction. And here comes perhaps the most important part of the work. Whether the model really knows that how gains affect perception for different kind of masker type. Thankfully, it seems to know that construction and traffic decrease Pearsonness as its gain is increased. And the bird tend to increase Pearsonness up to some level before it becomes too loud. And most importantly, that the model knows that when the masker is silent, that the prediction should not be dependent on the gain values. That is pretty much it for my proposed method. In this work, we propose a system for autonomous soundscape augmentation that takes acoustic context as an input and then predict perceptual quality for a particular masker gain combination by emulating soundscape augmentation in the feature domain instead of the audio domain using a modular design for efficient query. Thank you very much for listening to my talk. I will be having a poster session ICASSP P17 at Dome A on Friday 9th of June from 3:40 p.m. to 5:10 p.m. Thank you.